Dear students, in this session we will discuss about FM generation methods. Basically, FM generation methods are divided into two, that is direct methods and indirect method. Direct method is called parameter variation methods. Indirect method is also called Armstrong method. And under the direct methods, different methods are Varactor diode method, FM reactance modulators and linear integrated circuit, direct FM modulators. Here we are interested in Varactor diode modulators. Okay. First of all, let us see what is direct FM generation or parameter variation method. In the case of direct FM, actually it is a type of frequency modulation in which the frequency of the carrier is varied directly by the modulating signal. So, frequency of the carrier signal is varied directly by the amplitude of the modulating signals. And here the instantaneous frequency deviation is directly proportional to the amplitude of the modulating signal. That means based on the amplitude of the modulating signal, the instantaneous frequency of the carrier will be varying. So, that change in frequency or frequency deviation will be directly proportional to the amplitude of the modulating signal. Let us picturize that frequency modulator like this. See, here is a frequency modulator and here we will be applying modulating signal which is of lower frequency and a carrier wave which is of higher frequency, so that frequency modulator will produce FM signals. Let us see. And here this represents a simple direct FM modulator. You can see here that modulating signal. See, lower frequency signal here, it is seen that sound waves are the modulating signals. That means it is a low frequency signal. You know that sound wave has a smaller frequency. And there is a LC oscillator. You know, the oscillators are used to generate sinusoidal waves. So, LC oscillator will produce carrier signal which is of higher frequency. And here before the LC oscillator there is a tank circuit which is obtained by combining L inductor, a coil and a capacitor CM, that is a variable capacitor. And this capacitor will act as a microphone. Why it acts as a microphone? Let us see. Before that, this complete setup will act as a direct FM modulator circuit. So, here we are directly generating the FM signal from this carrier signal. That means the carrier frequency will be varied directly with the amplitude of this modulating signal. So, here the tank circuit is formed by inductor L and CM, and actually this part will be the frequency determining section for this LC oscillator. In the LC oscillator there will be a coil and capacitor. Similarly, at the outside there will be a tank circuit, that is CM and L, and this also determines based on the value of this, the frequency produced by this oscillator will be changed. And here the capacitor CM, it has got a capacity. That means whenever the input applied to this will be changed, there will be some changes in the distance between these plates. So, based on that there will be some changes in the capacitance value. Once the capacitance value is changed, the frequency produced by this oscillator will be changed. So, the capacitor microphone, that is CM, here this CM acts as a transducer. That means it converts sound energy to mechanical energy. As a result, there will be some changes in the plates of this capacitor. See, this is converted into mechanical energy, and this capacitor microphone contains two metal plates, and these metal plates, you know that the capacitor structure, that means capacitor contains two parallel plates, and those plates will be separated by a dielectric material. So, whenever there is a mechanical energy applied to this capacitor, the plate may be changed, or the distance between these two plates may be changed. So, there will be some changes in the capacitance value. Whenever this capacitance value Cm is changed, and this forms a part of this LC oscillator circuit. Once this capacitance value changed, the corresponding frequency generated will be changed. Okay, that means the frequency produced by this oscillator depends upon the value of this Cm. So based on the change in the value of Cm, there will be some changes in the frequency generated here. So this Cm value is changed based on the value of this sound wave. So whatever changes occur in the sound wave, that will be reflected in the Cm value. As a result, that will change the frequency of this LC oscillator. So we can say that we will obtain a direct FM output signal. That means basically it will produce a particular carrier frequency, but its value is determined by the value of this Cm, and that Cm change will be determined by Cm change is based on the value of the sound wave. That is why we are calling it as it is producing a direct FM signals. Let us see. Here the tank circuit L and Cm is the frequency determining section for the standard LC oscillator. Here the capacitor Cm act as a transducer. Transducer means that it will convert an energy from one form to another form. Here the transducer that converts the sound energy to mechanical energy. So we can say it as a capacitor microphone. Basically it consists of two metal plates insulated from one another, one of which can move in response to sound waves striking it. This causes small changes in the capacitance Cm, and parallel LC circuit in the oscillator portion determines the frequency of the carrier. The microphone is also a part of this parallel LC circuit. So a change in the Cm causes a change in the carrier frequency. The change in the amplitude of the sound wave causes a change in the carrier frequency. See, here change in the Cm causes a change in the carrier frequency. So indirectly we can say that a change in the amplitude of the sound wave causes a change in the carrier frequency. So here the frequency oscillation of the carrier generator is given by Fc is equal to 1 by 2 pi into root Lc. Next, this is the working of this a direct FM generator method. Next, in the direct FM generator, we are going to discuss about first method, that is Varactor diode modulator. And this Varactor diode modulator also produces FM signals. Let us see. You know that a Varactor diode is a type of diode which will be working in the reverse bias condition. Okay, let us see. See, Varactor diode is a semiconductor diode and whose junction capacitance varies linearly with DC bias voltage. And the symbol of the Varactor diode is shown here. Here you can see that it consists of a PN junction diode and there is double lines at this end side. You can see here there are double lines. It represents the capacitance value because it is highly dependent on the value of this capacitance. That means there will be a change in the capacitance value of this Varactor diode whenever the input voltage is changing. That is why Varactor diode is a semiconductor diode whose junction capacitance varies linearly with the DC bias voltage. Okay, and this Varactor diode is working in the preferably working in the reverse biased conditions. And see, we know that in the case of all diodes that exhibits a small junction capacitance in the reverse biased conditions, and in the case of Varactor diode it provides junction capacitance in the range of 1 to 200 picofarad, that is greater than that of the ordinary diodes. Let us see the basic principle of the Varactor diode modulator. See here. We know that in the case of FM there will be a modulated signal and a carrier signal. Usually in the case of FM generation, carrier signal is produced by the carrier oscillator that consists of a tank circuit, that will contain an L coil and a capacitor. And here it is again shown that there is a Varactor diode. Since it is a Varactor diode modulator, there will be a Varactor diode, and we will be applying the modulated signal to this Varactor diode. That is not a direct application. Let us go to the detailed circuit diagram in the next slide. And the modulated signal is applied to this Varactor diode, and but the here what happens is the capacitance of this Varactor diode will changes based on this modulating signal. So once its capacitance is changed, the overall capacitance of this carrier oscillator will be changed. As a result, the frequency produced will be changed. So based on the modulated signal, there will be different frequencies produced at the output of this FM wave. Okay, so let us see the detailed diagram. See, this figure shows the Varactor diode how we can use the Varactor diode to generate the FM wave. See, here at the input section we are giving the modulating signal and it is passed through a capacitor first and then the radio frequency coil, and next there will be R1 and R2 circuits which is used for biasing, and this RFC coil is used for this coil has high reactance at the carrier frequency that will prevent the carrier signal from getting into the modulated signal circuit. Actually this part of the section worked for modulated signal input. So if any higher frequency comes, this RF frequency coil will offer higher reactance to that RF signals, so that it will not be passed through this modulated signal circuitry. And R1 and R2 are biasing resistance that is used for providing particular biasing for the circuit. And the Varactor diode is shown here, and that is like the ordinary PN junction diode with a capacitor at one end, and there is another capacitor C, and also there is a tank circuit that represents the oscillator which will produce a carrier signal. L1 and C1 are the coil and capacitor or inductor and capacitor for that oscillator tank circuit. And the output is taken at this point, and this point is connected to the ground. All the sections are connected to the ground. Okay. Next let us see. Here it is given that L1 and C1 form the tank circuit of the carrier oscillator. The capacitance of the Varactor diode depends upon the fixed bias set by R1 and R2 and the AF modulated signal. Here the modulated signal is given as audio frequency signal, that is AF signal, that is audio frequency, because modulated signal frequency will be lower than comparing to the carrier signal produced by this oscillator tank circuit. So this Varactor, so the capacitance of the Varactor diode depends upon the fixed bias set by R1 and R2 and the AF modulated signal. So here is the Varactor diode, and at its this nth point, and this is P and this is N side. At the N side we are connecting the biasing circuit. So this biasing provided by this R1 and R2 and also the modulated signal voltage will be connected to the N side of this diode. So whatever signal is coming to this side will determines the capacitance of this Varactor diode. Okay. So based on the value of the voltage obtained at this point, the Varactor diode working will be changed, or its capacitance will be changed. Okay. And here there is an RFC radio frequency choke that has high reactance at the carrier frequency to prevent the carrier signal from getting into the modulated signal circuit. Let us see the working. And here first of all we are analyzing the case with the positive and negative cycles of this modulated signals. First we are assuming that the positive cycle goes through this part. So this will easily move through this part. Okay, this positive cycle easily moves through this part. Once this positive cycle comes to this side, see, you can see here that this is the N side of this diode, Varactor diode. Here positive cycle comes and here the ground section is there. That means here the voltage will be 0. That means P side is connected to 0 voltage and N side has a higher positive value. That means that this the reverse bias that will increases the reverse bias across this Varactor diode, right? For the diode to become forward biased, you know that P side should have a positive value of voltage and N side should have a negative voltage. That means P side should have a higher positive and N side should be lower positive. So the voltage at this point should be higher comparing to the voltage at this point for the PN junction diode to be forward biased. Here now we are assuming that the positive voltage comes to this side. That means N side is positive and this P side is connected to ground, 0 potential. So this diode will be reverse biased. That means when an external modulated signal voltage of positive cycle comes, that will add the reverse bias of this Varactor diode. Because of the changes, that means there is a change in the capacitance due to this reverse biased diode. When there is a change in the capacitance, that will affect the overall capacitance of this tank circuit. As a result, the frequency produced at this tank circuit will be different. Actually, this oscillator circuit is producing a frequency which is proportional to the carrier signal. Once a modulating signal comes, here the reverse bias at the Varactor diode increases. As a result, junction capacitance of this Varactor diode decreases. Reverse bias increases means that depletion region width increases. As a result, junction capacitance decreases. When capacitance decreases, we know that we have the previous equation that capacitance is inversely proportional to frequency. When the capacitance increases, the tank circuit frequency will be reduced. So, for the positive cycle corresponding, the reverse bias increases, the capacitance decreases, as a result frequency will be increasing. So, corresponding to the positive modulating voltage, carrier frequency will be increased. Similarly, when we are considering the case negative cycle, once negative cycle comes here, so the N side is connected, will be more negative. Here the ground is 0 voltage. When we are comparing 0 and negative voltage, negative is lesser. That means P side is more positive comparing to N side. That means this diode is forward biased. Once it is forward biased means that the junction depletion region in this PN junction will be reducing. As a result, capacitance value, junction capacitance will be increasing. When the capacitance increasing, we can say by the equation of frequency, the frequency will be reducing. So, for the negative cycle, the junction capacitance reduces and the diode is forward biased. For negative cycle, this Varactor diode is forward biased and the junction capacitance, the depletion region reduces and the junction capacitance increases. As a result, frequency decreases. So, in effect, we can say that for the negative cycle, the carrier frequency is reducing. So, there is a change in the carrier frequency based on the modulating signal, and that is achieved through the change through this Varactor diode, and that is by the change in the junction capacitance. Okay. So, let us see the working. The external modulating signal voltage adds to and subtracts from the DC bias, which changes the capacitance of the diode and thus changes the frequency of oscillation. At positive cycle of the modulating signal, the reverse bias applied to the Varactor diode increases. The capacitance as a result decreases and the carrier frequency increases. Okay. So, at the negative cycle of the modulated signal, the reverse bias across the Varactor diode decreases. So, the capacitance of that Varactor diode increases and the resulting carrier frequency decreases. And the center frequency of oscillator is given by Fc equal to 1 by 2 pi into root L1 into C1, where L1 and C1 is the capacitor and inductor values at the tank circuit, which is producing the carrier frequency. And with the modulated signal applied, the frequency is changed from F is equal to 1 by 2 pi into root L1 into C1 plus delta C. That means C1 is modified by C1 plus delta C, where delta C is the change in the Varactor diode capacitance. Sometimes it may be increasing or it may be decreasing. Based on that value, it will be positive or negative. Based on that value, the frequency will be changing. So, F is the new carrier frequency of oscillation here. So, that's all about this Varactor diode FM generation method. Thank you.